Hello everyone, welcome to Unacademy, which is the largest online education platform for GATE Computer Science and Information Technology. Here myself, Malesham Devasane. I'm going to take the classes for a theory of computation, compiler design as well as C programming on this channel. Here today we are going to see LL1 parsing, and also we will see main topic, which is how to identify LL1 grammar. And in the previous sessions, we have seen how to compute the first and follow set, then how to construct LL1 table. Right? We have seen many things in the previous class. Okay. Sorry guys. Okay. Let me introduce myself before starting the session. And myself, Malesham Devasane, I have secured all-year rank 119 and 210 in my GATE exam when I was giving in 4th year and 3rd year respectively. Then joined IIT Bombay to complete my MTech. Then I have almost 12 years of teaching experience. Here I am going to take mainly TOC compiler programming. In case if you are going to join an academy, and we are going to help you to crack the exam, and we have the structured courses, and we have many educators and many courses. So these are going to be the benefits for you. If you are going to take the subscription on Academy, there is no limitation how many times you sit, how many times you attend the classes. There are no restrictions like other people may have a restriction that how many times you watch the video, but we don't have any limitation. And we have it's just like entry is once, but access is unlimited. So this is what just entry control. Once you come inside the Unacademy, and you will have unlimited scope to learn every subject, guys. This is my referral code. DEVALIVE is to access any course from any educator, and this code will help you to get 10% discount, and also you will get a guidance from me to crack the GATE exam. So this is what the benefit of every code that we talk about. And usually I take C, TOC, compiler design, and algorithms also started on special classes which are free completely on Unacademy. But visit Unacademy to learn the classes or to attend my algorithms classes, which is completely free on a special classes. And if you want to attend a paid courses, definitely you must take the subscription, which we call plus or iconic subscription. And for that, what are the benefits we'll get? Like complete courses for complete course on every subject, like revision course on every subject, and crash courses, practice courses, and GATE previous year questions, solution courses, and doubt clearing, as well as test series. You have many courses for a single subject, so you will have a more scope to learn every subject inside the Unacademy. Right? This kind of benefits you will not get on any platform. That once you come inside the platform, you will have many things to learn one thing. So this is what the benefits from Unacademy, and you require the guidance. That is why you require the code to get into the Unacademy. If you use our code, we are going to help you how to prepare and how to crack the GATE exam. So this is what we require here. And if you look at the differences between plus and iconic, the plus, you will have live classes and weekly test and doubt solving sessions for every course that we launch. And iconic, all the benefits of plus, additionally a coach, additionally you will have a booster sessions, and additionally you have separate study material. Of course, you have many other things. What we are talking about here, they are all just minimum things. Yeah. Good evening, Sandeep. Good evening, Vaishnav. Yeah, if anybody watching this video, please like this session. And these are the very popular plans, like 1 year, 1.5, 2 years, and take more months, and you will pay less and you will get more benefits. So always remember, if you are coming for 1 year and you are actually preparing for more than 1 year, so take 2 years plan or 1.5 year for the plus subscription to get more advantages. Yeah. The payment is 27,225 for 1 year. You will have all the subjects from all the educators and unlimited access just when you pay 27,225 for 1 year. And similarly, you will have the 1.5 year and 2 years plan. So use referral code DEVALIVE to see that price after discount. And also we have two popular plans for Iconic, 1 year and 2 years. And advantages is, as I just spoken, that is about you will have a guide, you will have special sessions, and you will have separate study material. That is the advantage of Iconic. And here you will have 45,225 for 1 year and 66,600 for 2 years. And why do you require to pay more? Because of more benefits compared to the plus. And you will have other opportunity that you can join our Facebook group, so that anything that we want to update, we will update through the Facebook, and mainly we will update through a Telegram channel. So please subscribe to this channel, Unacademy GATE CS, so that you will get to access all the links, all the classes that we upload, that we update here. Yeah, we have various channels from Unacademy, like Electrical Electronics Instrumentation. We have Creatics GATE channel, and Unacademy GATE for mechanical, civil, and so many other benefits from Unacademy. These all are free YouTube channels. If you have any friends, please share with your friends to get the benefits maximum from Unacademy. Yeah, on this channel you will have all the subjects to learn, and please follow us, please like the sessions, and please subscribe to this channel if you have not yet done, and please like the session too, and share with your friends if you have anybody else. Yeah, good evening Satyajit. Yeah, good evening Gautam. Good evening. Yeah, thank you for joining the session. And in case if you are watching the video recorded one, please don't forget to like the session. And today we are going to look at, as I said, LL1 parser, but in previous classes also we have learned LL1 parser concepts, context-free grammar, about ambiguous, unambiguous derivation of a string using the grammar, and lexical analysis, and introduction to the compile. These are the previous sessions. Now in the last session mainly we have seen LL1 parser, and this is the second session on LL1 parser. So today we are going to see what is the LL1 parsing algorithm. In the previous class we have seen how to construct the table, but that's not enough. You must know what is the algorithm and how I can check the syntax of the given program, right? So today in this session I am going to help you, if you use the top-down parser, how your program will be compiled in the second phase, of the compiler. Okay, then we will go for how to identify LL1 grammar. First, let me recap. What is LL1 grammar, guys? LL1 grammar is a context-free grammar. I'm just revising, guys. What is LL1 grammar? It is the context-free grammar, no doubt. It is unambiguous grammar. And it must be non-left recursive. Then it must be left factored. Right. Other theoretical points are not covered here. So this must be unambiguous, non-left recursive, and left factored grammar. Unambiguous, also called as not ambiguous. You can say not ambiguous. And another one is not left recursive, but that is also same. Fine. That is, we have seen in the yesterday how to write LL1 grammar, but we have still, there is a question mark, how to identify LL1 grammar. Yeah, exactly, which can identify only one token. Good point, Sandeep. Now guys, how to construct LL1 parsing table? Yesterday in the previous session we have understood this point already. How to do that? We compute first set for every non-terminal. Every non-terminal, that is step 1, and step 2 we compute follow set. If any first set contain epsilon, in the step 1, compute follow set for that particular non-terminal. Then third, give entries properly. First, make entries for the first set. Make entries make entries using first set. So find out the corresponding production that has first set. Then if you see epsilon in any first set, then make null entries, that null rule entries. Using follow set. But null rule may be epsilon or maybe some other production, but that can derive epsilon, either direct or indirect null. So this was the yesterday concept. In case if you have multiple productions in the same cell, then the given grammar is not LL1, because sometimes we fail to identify the given grammar is LL1 or not with the theoretical concept. So you require to consider the table, guys. Okay, let's move on. So for this grammar, and somehow we computed in the previous session, right, how to give entries. Is that clear, everybody? So if you want to learn, you can also do it again, but we have done in the previous session. So I believe you are good at constructing the table now. Okay. Next one. See, the LL1 table we have seen only one way. We are constructed using this model, the first one, guys. But you can use this one, or you can use the third one, or you can use the fourth one, you can use the fifth one. There are many representations for LL1 table, but the first kind of LL1 table is easy, and that is easy to compute the size also, but remaining the sizes are going to vary, guys. You have to look at the representation. Yeah, good evening, Vaibhav Gupta. Look at now, and somebody has constructed the first one, guys. Look at that. We know this one. We know we have used this one. And how to represent the second one? Just write this RHS only. We don't need LHS. Why we don't need LHS? Because LHS is already there as a row name. Can you see, guys? S means S productions. L means L productions. So LHS of a production is not compulsory, so that you can save the space to store inside the table. So that is the one advantage you have. But there are other tables also we have. Like, why do you want to store the production in the table? You can number them. Number the productions. Production number, rule number. And instead of a rule, instead of a production, you just give a number of that production in the table. So here, the first production is the 1. And this production number is called as 2. And this production number is called as a 3. And if any production coming twice, so now give the number accordingly. Yeah. Is it clear? So same entries you can map, like 1 is a mapping to the production, you can say that. The 1 can be called as an address of S derives A. 2 is called as an address that S derives open parenthesis L closed parenthesis. Everybody? So this is how you can implement or represent a table. That is, next one is the fourth one. Instead of constructing rows and columns like non-terminals and terminals, you can do other way. So we have only columns to represent now. What non-terminal and terminal is going to derive the first symbol. This is the first symbol. The terminal derived as the first symbol. If S derives A as the first symbol, this is basically row in the previous table and column in the previous table. And this is the entry of the table. So all of them you can put in a list wise. What is this? A row, and this is the column, and this is the entry. So all of them you can put as the columns now. So have a clarity what I am trying to speak here. The previous table, when you look at it, we have a row and we have a column and we have an entry. Yes or no? So all of them you can display as a list. Yeah. So now S production, that is S non-terminal, can derive A as the first symbol using S derives A production. Similarly, how many entries we have? How many entries we have, guys? How many entries we have? If you count it, you can look at how many entries we have. 1, 2, 3, 4. So we will have 4 rows, that's all. Every entry there is a corresponding row and column combination. Yes. This is another representation of the same LL1 table. And fifth one, you can use the numbering of productions. There's the first one and the second production. You can map it directly. You can map it. You can map it instead of writing whole production. So there are various number of ways to represent a table. In the exam, you really do not know how are they going to ask. So please do not confuse, follow as per their representation and understand what we require in that question. Yes. Is it clear? So you must aware of that. Even though we construct this representation, guys, this is a standard one. This is a standard one. But there are other representations for the same table, guys. All right. Now let's move on to the how to parse given input using LL1 parser. How to parse, guys? Yeah, good evening, Jayesh. How to parse given input? How to parse given input? And what is the meaning of parsing? Parse basically here indirectly deriving. How to derive given input? Derive nothing but how to verify given input, right? So it's just like how to verify the given program syntax indirectly, but with the help of top-down parser. Now let me talk about, if you want to understand the parser, guys, how many things are required to understand? Did you remember the concept? We require stack, we require input, we require table, we require some algorithm to follow. This many things. Right now we have table and we have input that must be given, and we have a stack. But what is algorithm to understand whether the given input is syntactically correct or not? Your input is maybe like your program, maybe AAB. AAB is just not characters, guys. They are going to be tokens. They are going to be your program tokens. AAB is your program. You may call it as a now string, but actually it is a program converted into 3 tokens, right? And somebody asked, sir, why do you require the dollar? Because we are going to do something like, I will start with S and dollar. If S derives this AAB, then only dollar left at the end. So dollar on the stack, and the head, when it moves to the dollar, only on the stack this dollar is exist. All the things that we do on the stack will be deleted. So this is why we require the dollar as the end of the S. After S, why we take a dollar? Because when S derives your input, then somehow this dollar we are going to check. Yes is going to match with AAB, then we will work on the dollars to understand our syntax. Okay, we will understand slowly that too. And here we have a parsing algorithm, and we have output. Output is a parser, you can assume LMD. LMD, guys, parse tree or leftmost derivation that we are going to produce. And parsing table, just now we have constructed LL1 parsing table because we are following LL1 parsing, right? Then how to use a stack, really we do not know now. I will explain that. How to use a stack, how to use the table already built, how to use the table to understand given input. Everybody clear? So now we have the questions. How to use the table. Then parsing algorithm will explain. Then how to perform operations on stack, how to use the stack, and how to read an input, how to read your program, input program. All the things are going to be understood with algorithm, that is parsing algorithm. I may say it's LL1 parsing algorithm or program. Yeah. So LL1 parsing algorithm is going to talk about all of them, and it is also going to produce the parse tree when the input is successfully scanned, and it is also going to produce the syntax error in case if any problem comes. Okay, let's begin to understand this parser. Is it clear? There are two actions we are going to do, guys. There are two actions. One is the prediction, another one is match. Prediction is basically will help us for the substitution. And match is going to help us to do something in the algorithm. We will see that. Whenever we predict, that means we found a correct rule to take the substitution. So what is the meaning of the prediction here, guys? Example like this. Don't worry about algorithm now. Suppose you have some non-terminal and here we have a terminal. Right now we are pointing to this and top of this stack is X. Then we are going to look at the table. Okay, in the table, M means table name, guys. The top of the stack, comma input, that is, how do you look at it? That M of, that is X comma T. If you have any production like X derives some alpha, that is the entry into the table, guys. Already you built a table that X under T, you might have some production X derives alpha. Then what's going to happen, guys? We have predicted what production we need to substitute. That means we are going to substitute with alpha. So X we are going to delete. The first action, the first step in the action is going to be pop X. The first action is going to be pop X. Second one, push pop X and push alpha in reverse. Why reverse? Guys? Because we want to scan left to right. Suppose here you have A, B. Then if you push this capital A, that goes bottom. So we don't want to do that. So we will push in the reverse order. So capital A comes first so that we can scan left to right. So push your RHS in reverse order. We will see that. So what is the prediction? When we predict, that means in the table we found an entry that is a production. That production, what it is going to tell us, okay, the LHS is on the stack. This is LHS is on the stack. Now RHS we need to replace. The RHS is there in the table. And RHS we are going to push in the reverse direction. Is that clear? Pop LHS, that is a pop top of the stack, and push RHS in reverse order. That RHS is there in the table. Everybody? Yeah, that is the prediction. Okay, now what is the match? Match, guys, when the top of the stack is some terminal is there, and here also terminal is there, then we don't look at the table. In the table, you know that the table we have rows as the non-terminal. So what we are going to look at, we never look at the table, right? So if top of the stack, this is the top and this is the input. If the top of the stack is equal to input, then what we do is equal to input. First one, pop the top of the stack, that is the T, and second, increment head. Because there is head, we can move to the next. That means we derived one token using our grammar indirectly. We can increment our head, so it can point to the next token to understand. That is what LL1. It is going to look at one token at a time. Can I derive a T? If I can derive the T, then I increment the pointer. I do something else in my grammar. Yes. That's clear? Okay, don't worry much about it. We are going to practice it. Okay, it looks like I'm doing abstraction, so don't worry about this abstract details. This entire theory is going to be explained clearly with an example. Okay, so this is an algorithm that I'm going to apply, so don't worry much about it. Whenever top and input is equal $, that means our program is scanned completely and there is no syntax error. That's what I told in the beginning. When you reach the $, and the top of the stack is also $, then our scanning is over, no syntax error. So that is ultimate goal for us, and this is the final goal. If that is not, top of the stack is equal to input, that means we don't look at on the table in the table, guys, because top is equal to input, because both are terminals. Then what we do, pop top of the stack and advance to the next token, that is next input symbol, and then repeat the step again, right, until accept. Now top of the stack is non-terminal, then definitely go to the table, look for the row and column. Row is the top of the stack and column is an input. If you see any production that is, let's say, X to alpha, then replace the top is LHS basically, with a production in reverse order, alpha in reverse order. Everybody, then do again these 3 steps, verify in a sequence again and again till you accept. Yeah, so this is our algorithm. Still remembering all these 3 steps looks very difficult right now, so let's start algorithm. Okay, this algorithm I kept in mind, then I will explain every time what I am going to do. So I will help you here. This is called as, remember that, this is called as the third one. This is called as a prediction. I will write a prediction. Second one is called as a match. The first one is called as accept. So we are going to take the 3 actions. Prediction, match, but in the last step we will get accept. If not, that is error. Okay, this is the fourth one. So there are total 4 actions will be taken. 4 actions: prediction, match, accept, error. Right? So accept or error is going to be the final goals. If the program has any problem, we will produce an error. Otherwise, accept. Let's begin. So initially, who is there on the stack? We always start with, guys, dollar. Okay, let me use dollar. And then S beginning. So this is our initial configuration of the stack. And what is our input? Input that you have written already, some program. This is our program. And what is the action that we are going to decide now? Now tell me, guys, quickly. The previous algorithm looks very difficult to understand, but now you can do that. What action I am going to take? Look at, guys, every time I do, that is, go to the table. This is the table name. Go to the table, look for top of the stack and open parenthesis. Now always point. This is the top of the stack and this is your current input symbol, guys. Yes, comma, left parenthesis, and at the end of the input keep the dollar to accept if the program, your input, is syntactically valid. Okay, let's begin. S comma open parenthesis. Which one? S is the non-terminal, right? When top of the stack is non-terminal, always we go for prediction. Always we go for production. Prediction, production, substitution, all are same now. And we have prediction. We have prediction now. Prediction. This is our action. The prediction is what? We have found a production. What we do here? We pop S and we push that RHS in reverse order. Then how do you see that? Okay, dollar already there. S is popped. Then push in reverse order. Closed parenthesis, L and left parenthesis. Is that clear? You must push the RHS in reverse order. Everybody, now look at. Now, who is the top of the stack right now? Who is the top of the stack right now? Now, top of the stack is equal input. Of course, that is not a dollar. If it is dollar, accepted. Now, both are equal. So, what you do? And we are going to pop. Pop it and increment the head to the next token. So, what do you see now is the dollar closed parenthesis L. Now, what do you see here? Open parenthesis A closed dollar. And already there was open parenthesis which was scanned completely. Now we understood your grammar, your compiler can derive that syntax. Now we have L. Every time I'm writing here. Now we have top of the stack L. L is the non-terminal, so you must go to the table. Whenever non-terminal comes at the top, you must go to the table only. And open parenthesis is the next token. Right? Now L comma open parenthesis, we have this production. Again we got prediction. Previously we got a match. And now we got a prediction. Match, what we did? We have popped and we have incremented the pointer. Now prediction. Prediction, which prediction we have? There is a production. What do you do? Pop LHS, that is pop top of the stack. We do that. Pop top of the stack and push the RHS in reverse order. Can you do that very quickly? Dollar close parenthesis and push. Okay, closed parenthesis S and left parenthesis, reverse order. And now guys, Now top of the stack is closed parenthesis. Now I'm writing, guys, top of the stack is closed parenthesis, that is also, sorry, open parenthesis, that is also matching with the input. This is the top of the stack and this is the input. Both are matching, so we got a match. We pop and we increment. We pop and we increment. So now we have dollar, closed, closed and S, and we have A, closed, closed and dollar. Now we have to look at top of the stack. Top of the stack is non-terminal. So what happens? S, comma, A. You are going to look at in the table. We have a production, that is S derives A. We got a prediction now. This is the prediction. We are able to predict correctly. If you see that blank entry, there is no production, immediately syntax error. If you don't have any production there, you went to S derives A, but there is no production, immediately an error, guys. That's called as syntax error, you can say that. Now what we do, we pop S and then we push LHS, RHS in reverse order, right? Yeah, dollar, closed, closed, and that is A only. And now this time match happens. Match. You know what is that? A is match. So we pop top of the stack and we increment the pointer. Everybody? And now again match. Again match, like top of the stack is equal to input. Again top of the stack is equal to input. Then what we do? We pop top of the stack, one of the symbol, and we increment our head. Then close parenthesis, closed, again match. Again match. Now we have dollar, dollar. So dollar, dollar, we know it is an algorithm, we accept. Yes. So slowly, but is it really important for the exam? Not at all. But what is important? Okay, this is nothing but a practical implementation of LMD, guys. This is nothing but practical implementation of LMD. How this is a practical implementation? Look at, if you start with S, and what you have done, the first prediction is L, and the second prediction, you can see that S, and the third prediction we have seen A. Okay, whatever, here you can do that. We have derived here. So in LMD, first you substitute, and here you can't see LMD RMD difference. The reason is only one non-terminal is there in every sentential form. Okay, so this order is called as LMD order. So whatever you have done is actually LMD algorithm. LMD algorithm. So it can understand when to substitute according to LMD order. Yes. Now don't worry much about it, because the questions from here is I have not seen, and maybe we'll also not see this kind of questions. Okay. Then there are two kinds of conflicts. This can be possible. T conflicts and conflicts, guys. Suppose you have, let me do something, guys. Here that example will not help you. We need something else now. Okay. So instead of this one, let me take some other example to understand what is T conflict. T conflict is that on the top of the stack, you have some terminal we have like a token. On the input also we have some terminal, that's input, right? You can assume this is now top of the stack, and top of the stack is terminal, but it is not matching. Top of the stack is terminal, but it is not matching with input. Top not equal to input. That means you got a T conflict. When this could happen, it could happen like, you have S derives AB and you have written AC. It looks like in the table when you start with $S, let's say this is an input, and $S and S under A, you will definitely have AB production. So S will be replaced with BA in the reverse order. So what do? A will pop and increment, then C and B doesn't match. C and B doesn't match. So C not equal to B. Now table will not help you. Only we will produce T conflict. T conflict. The top of the stack is terminal and that is not matching with your token. That means you have the T conflict. Now, when do you get N conflict? N conflict, it happens, you went to the table, but you know, these are called as the blank entries, basically called as errors only. If you are going for any blank entry, then like example, M, the top of the stack is a non-terminal. This is non-terminal. So definitely you should go to the table, and input is the column. Input is the column. Remember guys, this will be top of the stack and this is your input. That has blank. Blank means error. So that this error is called as N conflict. Whether it is T conflict or N conflict, your parser will produce syntax error, guys. Your parser will produce syntax error. Okay. Now I hope you understood the parsing algorithm, and that is a whole theory is about leftmost derivation practical implementation. Now we are going for the most important question for the exam point of view. How to identify LL1 grammar? As I said, apply theory and construct the table or use shortcut. But all of them, if you compare all of them, the second and third will work properly. The first you may fail sometimes. When you are applying the theory, sometimes within seconds you can answer, sometimes you can't. Then you must go for either shortcut or constructing table. But constructing table takes time, so we go for shortcut. We have a shortcut to identify LL1 grammar. So before concluding how to identify, let me tell you, if any entry of the table we have multiple entries are defined, right? Multiply there are entries defined, then the given grammar is not LL1. Given grammar is not LL1. We know that. If you go to any entry of the table, if you see more than one production, definitely that grammar is not LL1. We know this. But why that multiple productions are there in the same cell? Why multiple entries happened in that combination? Because there could be many reasons. The grammar can be ambiguous. Any one of the reason, guys. Grammar can be left recursive. Grammar may not be left factored, and there could be other reasons also. And most of the people don't know if they have unambiguous, if they have non-left recursive, if they have left factored, they might assume the grammar is LL1, guys. It's not true. And there might be other cases as well. That I'm going to help in this session how to identify LL1 grammar theoretically too. But reason not easy theoretically. Reason is not easy. So applying theory is beneficial to save the time. But if you are not able to apply the theory, then you must choose either shortcut or table construction. But table construction takes more time, so you can go for the shortcut. Okay, so let's start one by one. What is this shortcut? So that I will help you later on how to verify. What is the shortcut we have? Shortcut, we have two rules, guys. Any production has, or any non-terminal has two productions, more than two is fine. Then what do you do blindly? Just do first of alpha 1 intersection first of alpha 2. Just do that. In case if you see not empty, then immediately you say given grammar is not LL1. So if you want to say LL1, then equal to empty for every combination of alpha 1 and alpha 2. So this is one we have. If you want to say LL1 equal to empty, if you want to say not LL1, then not equal to empty. So not equal to empty is enough to answer not LL1, but equal to empty, just don't do only for alpha 1, alpha 2. We will verify. Example, guys, suppose you have A2, A, B and AC. Then guys, you have to apply for this two first, empty, and this two empty, but this two, first of A intersection, first of AC is not empty because small a is the common to them. And this is not LL1. It is not LL1. But if you want to say LL1, you have to check every two productions, their first set's intersection must be empty, right? Saying LL1, you will take much time, right? For all I comma j, that is I not equal to j, remember, the first of alpha I intersection, first of alpha j must be empty, then we say LL1, then we say that productions are in LL1. So this is slightly difficult to check every combination, so we do opposite way. Yeah, this is a shortcut, and how to apply it we will see that. Rule 2, in case you have a null production, then you have to apply first of alpha, but here because of epsilon, don't take the first, it depends on the after a, follow of a, then that is not equal to empty, then LL1, then not LL1, sorry, then not LL1. Everybody, then not LL1. Okay, if you want to say LL1, so you have to be very careful. Suppose you have A or B or epsilon, it to clearly empty to hai, but these two are difficult right now because one of the combination depends on the follow set. First of A intersection follow of capital A, first of small b intersection follow of capital A. So you have to check all of them to say LL1. Okay, so let's apply this algorithm slowly to understand. So now we have so many examples. Now let's look at how the theory works. Of course, table we can't design, and shortcut we can do always. And what is the problem with the theory? Sometimes when you identify this like this, okay, left recursion is visible, and anywhere else, yes, left recursion is visible, and left recursion is visible, and left recursion is visible. Of course, when left recursion is there, don't worry about ambiguous. Left recursion is visible, right? All of them directly you can say not LL1. Not LL1. Look at that. Without using shortcut, I am able to say not LL1. That is easy. Shortcuts are sometimes easy to apply, right? Okay, now theory is easy to apply. Shortcut takes time. Look at now. Shortcut. I am applying shortcut. Okay, first I will apply this too. What is that? Okay, first of, that is open parenthesis L closed, intersection first of A. Is it empty or not? Here open parenthesis comes, here A comes, it is empty. मतलब यहाँ पे तो problem ही नहीं है. But don't conclude LL1 because you need to check this too. And here, if you do that, the first of LS intersection first of S, and first of LS, L से S आएगा, S से दोबारा आपको open parenthesis comma A, and first of S जो है वही आएगा यहाँ पर. So this is not equal to pi. It means it is not LL1. This condition fails. That is, the first of LS and S have the common terminals. Yes. Okay guys, if you're watching this video, please keep liking the session. Yeah, please do that guys. Next one. Single production, no need to check at all. Always LL1. Single production is always LL1, remember guys. But two productions, look at first of this one and first of this one. That is first of AA intersection first of B. Is it equal to pi or not? Yes. So this also has no problem. Now we say LL1. Every combination we check, then we conclude LL1. But not LL1, no need to check everyone. Whenever you have a problem that is not equal to pi, then say the answer. Now, combination 1. Agar answer aa gaya na, don't do anything else guys. Don't do anything else. Look at this. For this combination, first of AS intersection first of SA. Is it equal to empty? Check it. Here you will get A intersection first of S. Definitely you will have A there and epsilon also there. But there is not equal to pi or not? Yes. So directly not LL1. No need to check other combinations, like no need to check these two combinations, no need to check this two, which will waste our time, because already you know there is a problem. What problem we have? When you are looking for A, that is from S, when you are looking for A, you will have this production, you will also have this production. That is the reason A came from the both productions as a common first symbol. Okay. Now, fourth one, and again I am applying this too. And in future, if you get not empty, then you have to apply every other combination too. And same concept guys, first of AS intersection first of SA. And is it not equal to empty again? Yes, because first of S you will again get A only will get now. A only will get, epsilon is not there. So you will have a common terminal, not LL1. And there is another shortcut also we have, that is ambiguous and left recursion. So many concepts are there in that grammar guys. If any non-terminal participating in both left and right recursion, the grammar is not LL1. Yes or no? If any non-terminal participating in both left and right recursion, then the grammar is not LL1. Is it clear? Okay. Now this one, people know that it is ambiguous, left recursion. Theoretically, you know many answers. Left recursion, so definitely not LL1. Definitely. Okay. Now what I am going to talk about, principle, our shortcut. When I apply this one, first off, you will get common terminal. How? First of SS intersection first of S. And you will get something like first of capital S, again same as whatever you have there, intersection open parenthesis comma A. This is not equal to pi. So again this is not LL1. Not LL1 is always easy to say guys. And next one also will produce the same. First of this one, here E is there, so definitely we'll get the common terminals. So it's again not LL1. Okay, seventh one. Now you have to apply this too. And when you do that, first of AB intersection first of A. Here A is coming. Here A is there. So it's not equal to pi. So this is also not LL1. And eighth one guys, you can see now, okay, I is here. So it is a common prefix, right? Directly you can say it is not LL1. Everybody, it is not LL1. So rule 1 we are applying. Sometimes you require rule 2. Because of epsilon. Okay, this is how quickly we can identify LL1. That is just we can apply the shortcut, you can apply it. And I have a doubt. Okay guys, now we have a very good conclusion, a very important conclusion. That is, guys, I'm trying to show something. Maybe you will surprise by looking at this. And look at this. ES2 AB. A derives A, B derives B. And consider this is the one grammar guys. Consider this as the one grammar. I want to conclude something from all these examples guys. And second example, I'm going to do something. This is another grammar. Okay. Now S A or AB. Okay. There is another one which is very dangerous, that very less people understands here. That is, yes, derives A, S, A or epsilon. And look at all these grammars guys. Look at all these grammars. And you know there is a lot of difficulty in understanding guys in this kind of concepts. Everybody knows one answer guys. That is this is not LL1. This is also not LL1. But I want a proper reason for every case guys. Not LL1. And this grammar is what? Because of ambiguous. And when you look at, is it left factored or not? No, it's not left factored, because this A also comes here and not left factored guys. What is the main reason here? Left recursion. But no ambiguous here. And what is the main reason here? Common prefix. Guys, common prefixes are there everywhere basically. Here A is there, here A is there. Here also B is there, here also small b comes. Here also B comes. And here also A small a comes. And here, guys, the common prefix is there everywhere. But only the last one, which is the very special grammar, when there is no null production and answer is straightforward. Okay, if the grammar is not left factored, definitely not LL1. Is that clear? These all are non-left factored grammars. So definitely they are not LL1 too. But the last one, it looks like a very different, guys. The reason is it is not ambiguous, no left recursion, no common prefix to, guys. When you look at one length, but it is not LL1, there is no reason matches. Now you can't say ambiguous, now you can't say left recursion, now you can't say even the non-left factored, guys. There's a very special grammar in the LL1 grammars. Special grammar. Why special? It is, what is it is? Unambiguous, very clear. It is non-left recursive, very clear. But there is a common prefix is there indirectly, but we don't say that. It is also left factored, no doubt, but still it is not LL1, guys. Still it is not LL1. The reason is it has some other concept inside which is hiding. Because of null production, you are not able to see there is another production which is going to derive A as its first terminal. Here also A is coming as the first, but you can't see that. You can't see that. The theory fails to explain why A is coming in place of epsilon. Why? Because whenever epsilon is there, we always compute their follow of S. When there is a follow of S, small a comes. That means here also A is there. But you can't see through the left factored concept, or that is left factored grammars and other grammars, guys. So this is the very special concept in our the LL1 grammars. So I have a clarity in this, guys. Very less people know about it. I want you to understand clearly and never ever say that the grammar is left factored. It doesn't mean that grammar is LL1. Remember, but if the grammar is free from epsilon, no null production is there in the grammar, that point is true. If we have no null production, if no null production in the grammar, you can guarantee that every non-left factored is the not LL1. Every left factored you can assume it is LL1 if there is no null production. But if there is a null production, your theory fails, but formula and table will succeed, guys. You can either apply the formula or you can go for the table to understand this problem. But theory can't help you why this grammar is not LL1. It looks like no ambiguity. It looks like no left recursion. It looks like no common prefix. But still it is not LL1. Still it is not LL1, guys. Okay. Today we have understood until now what is LL1 parser. And LL1 parser is not powerful because of it can represent a less number of structures compared to the LR parsers. So using top-down parser, we may not represent most of the syntaxes. So we require the powerful parser to represent more structures in our programming languages. So next session, I'm going to start bottom-up parser. Then I will conclude what is the difference between top-down and bottom-up. And we will have a clarity how to understand the syntax analysis with the help of bottom-up parser. And I hope these sessions may be short, but which have every detail you require, guys. Remember that it is not the crash course, even though it is crash, but I am not teaching like a crash course. Every detail is coming into this. Only the thing is how, whenever you have the doubt, you are not able to ask because of I'm not waiting here. And if you have any doubt, please visit Unacademy and ask me your doubts, because this is my profile. You can attend my classes freely anytime. You can ask your doubt. I will keep helping you to understand any concept that I am teaching right now. And please visiting my profile and keep asking doubts in my free sessions. And if you are interested, please take the subscription and use DEVALIVE is my referral code. DEVALIVE is my referral code. It's most probably you will get gate rank if you take the subscription. Of course, even you don't take the subscription, you can do that, but guarantee is not there. Okay, so C programming, TOC compiler I am taking, and CO and DS Vishwadip sir, and OS Khalil sir, and discrete mathematics DBMS Satish sir, and C and Pankaj sir, and machine learning is Arun sir. And before leaving this session anytime, please don't forget to like this session and also please share it with your friends and subscribe to this channel to get daily notifications or regular notifications from us. Thank you so much for attending today's session, and keep attending our live sessions and keep asking your doubts and keep following our classes. Thank you so much. Bye bye. Take care. See you.